Learning objectives. In this chapter, the user will learn the following in detail: properties of light, intuitive color concepts, RGB color model, YIQ color model, CMY color model, HSV color model, conversion between HSV and RGB models, HLS color model, CMY color model. A color model defined with the primary colors cyan, magenta and yellow, CMY, is useful for describing color output to hard copy devices. Unlike video monitors, which produce a color pattern by combining light from the screen phosphors, hard copy devices such as plotters produce a color picture by coating a paper with color pigments. We see the colors by reflected light as subtractive process. As we have noted, cyan can be formed by adding green and blue light. Therefore, when white light is reflected from cyan-colored ink, the reflected light must have no red component. That is, red light is absorbed or subtracted by the ink. Similarly, magenta ink subtracts the green component from the incident light, and yellow subtracts the blue component. A unit cube representation for the CMY model is illustrated in this figure. In the CMY model, point 1, 1, 1 represents black because all components of the incident light are subtracted. The origin represents white light. Equal amounts of each of the primary colors produce grays along the main diagonal of the cube. A combination of cyan and magenta ink produces blue light because the red and green components of the incident light are absorbed. Other color combinations are obtained by a similar subtractive process. The printing process often used with the CMY model generates a color point with a collection of 4 ink dots, somewhat as an RGB monitor uses a collection of 3 phosphor dots. 1 dot is used for each of the primary colors, cyan, magenta and yellow, and 1 dot is black. A black dot is included because of the combination of cyan, magenta and yellow inks typically produce dark gray instead of black. Some plotters produce different color combinations by spraying the ink for the 3 primary colors over each other and allowing them to mix before they dry. We can express the conversion from an RGB representation to a CMY representation with the matrix transformation as shown, where the white is represented in the RGB system as a unit column vector. Similarly, we convert from a CMY color representation to an RGB representation with the matrix transformation as shown, where black is represented in the CMY system as the unit column vector. Conversion between HSV and RGB models. If HSV color parameters are made available to a user of a graphics package, these parameters are transformed to the RGB settings needed for the color monitor. To determine the operations needed in this transformation, we first consider how the HSV hex cone can be derived in the RGB cube. The diagonal of this cube from black, the origin, to white corresponds to the V-axis of the hex cone. Also, each subcube of the RGB cube corresponds to a hexagonal cross-sectional area of the hex cone. At any cross-section, all sides of the hexagon and all radial lines from the V-axis to any vertex have the value V. For any set of RGB values, V is equal to the maximum value in this set. The HSV point corresponding to the set of RGB values lies on the hexagonal cross-section at value V. Parameter S is then determined as the relative distance of this point from the V-axis. Parameter H is determined by calculating the relative position of the point within each sextant, which is an instrument used to measure the angle of the hexagon. An algorithm for mapping any set of RGB values into the corresponding HSV values is given in the following procedure. We obtain the transformation from HSV parameters to RGB parameters by determining the inverse of the equations in RGB-TO HSV procedure. These inverse operations are carried out for each sextant of the hex cone. The resulting transformation equations are summarized in the following algorithm. HLS color model. Another model based on intuitive color parameters is the HLS system used by Tektronix. The HLS double cone representation is shown in this figure. The three color parameters in this model are called hue H, lightness L, and saturation S. Hue has the same meaning as in the HSV model. It specifies an angle about the vertical axis that locates a chosen hue. In this model, H equals 0 corresponds to blue. The remaining colors are specified around the perimeter of the cone in the same order as in the HSV model. Magenta is at 60 degrees, red is at 120 degrees, and cyan is located at H equals 180 degrees. Again, complementary colors are 180 degrees apart on the double cone. The vertical axis in this model is called lightness, or L. At L equals 0, we have black, and white is at L equals 1. Grayscale is along the L axis, and the pure hues lie on the L equals 0.5 plane. Saturation parameter S again specifies the relative purity of a color. This parameter varies from 0 to 1, and pure hues are those for which S equals 1 and L equals 0.5. As S decreases, the hues are said to be less pure. At S equals 0, we have the scale. As in the HSV model, the HLS system allows the user to think in terms of making a selected hue darker or lighter. A hue is selected with the hue angle H, and the desired shade, tint, or tone is obtained by adjusting L and S. Colors are made lighter by increasing L and made darker by decreasing L. When S is decreased, the colors move towards gray. HSV color model. Instead of a set of color primaries, the HSV model uses color descriptions that have a more intuitive appeal to a user. To give a color specification, a user selects spectral color and the amounts of white and black that are to be added to obtain different shades, tints, and tones. Color parameters in this model are hue H, saturation S, and value V. The three-dimensional representation of the HSV model is derived from the RGB cube. If we imagine viewing the cube along the diagonal from the white vertex to the origin black, we see an outline of the cube that has the hexagon shape shown in this figure. The boundary of the hexagon represents the various hues, and it is used as the top of the HSV hex cone. Refer the next figure. Hue is represented as an angle about the vertical axis ranging from 0 degrees at red through 360 degrees. Vertices of the hexagon are separated by 60 degrees intervals. Yellow is at 60 degrees, green at 120 degrees, and cyan opposite red at H equals 180 degrees. Complementary colors are 180 degrees apart. Saturation S varies from 0 to 1. It is represented in this model as a ratio of the purity of a selected hue to its maximum purity at S equals 1. A selected hue is said to be 1/4 pure at the value S equals 0.25. At S equals 0, we have the gray scale. Value V varies from 0 at the apex of the hex cone to 1 at the top. The apex represents black. At the top of the hex cone, colors have their maximum intensity. When V equals 1 and S equals 1, we have the pure hues. White is the point at V equals 1 and S equals 0. This is a more intuitive model for most users. Starting with a selection for a pure hue, which specifies the hue angle H and sets V equals S equals 1, we describe the color we want in terms of adding either white or black to the pure hue. Adding black decreases the setting for V, while S is held constant. To get a darker blue, V could be set to 0.4 with S equals 1 and H equaling 240 degrees. Similarly, when white is to be added to the hue selected, parameter S is decreased while keeping V constant. A light blue could be designated with S equals 0.3, while V equals 1 and H equals 240 degrees. By adding some black and some white, we decrease both V and S. An interface for this model typically presents the HVC parameter choices in a color palette. Color concepts associated with the terms shades, tints, and tones are represented in a cross-sectional plane of the HSV hex cone. See this figure. Adding black to a pure hue decreases V down the side of the hex cone. Thus, various shades are represented with values S equals 1 and 0 is less than or equal to V is less than or equal to 1. Adding white to a pure tone produces different tints across the top plane of the hex cone, where parameter values are V equals 1 and 0 is less than or equal to S is less than or equal to 1. Various tones are specified by adding both black and white, producing color points within the triangular cross-sectional area of the hex cone. The human eye can distinguish about 128 different hues and about 130 different tints, saturation levels. For each of these, a number of shades, value settings can be detected depending on the hue selected. About 23 shades are discernible with yellow colors, and about 16 different shades can be seen at the blue end of the spectrum. This means that we can distinguish about 128 into 130 into 23, 82,720 different colors. For most graphics applications, 128 hues, 8 saturation levels, and 15 value settings are sufficient. With this range of parameters in the HSV color model, 16,384 colors would be available to a user, and the system would need 14 bits of color storage per pixel. Color lookup tables could be used to reduce the storage requirements per pixel and to increase the number of available colors. Intuitive color concepts. An artist creates a color painting by mixing color pigments with white and black pigments to form the various shades, tints, tones in the scene. Starting with the pigment for a pure color or pure hue, the artist adds a black pigment to produce different shades of that color. The more black pigment, the darker the shade. Similarly, different tints of the color are obtained by adding a white pigment to the original color, making it lighter as more white is added. Tones of the color are produced by adding both black and white pigments. To many, these color concepts are more intuitive than describing a color as a set of 3 numbers that give the relative proportions of the primary colors. It is generally much easier to think of making a color lighter by adding white and making a color darker by adding black. Therefore, graphics packages providing color palettes to a user often employ 2 or more color models. One model provides an intuitive color interface for the user, and the others describe the color components for the output devices. Properties of light. A color model is a method for explaining the properties or behavior of color within some particular context. No single color model can explain all aspects of color, so we make use of different models to help describe the different perceived characteristics of color. Properties of light. What we perceive as light or different colors is a narrow frequency band within the electromagnetic spectrum. A few of the other frequency bands within the spectrum are called radio waves, microwaves, infrared waves, and X-rays. This figure shows the approximate frequency ranges for some of the electromagnetic bands. Each frequency value within the visible band corresponds to a distinct color. At the low frequency end is the red color, 4.3 into 10 to the power of 14 Hz, and the highest frequency we can see is violet color, 7.5 into 10 to the power of 14 Hz. Spectral colors range from the reds through orange and yellow at the low frequency end to greens, blues, and violet at the high end. Since light is an electromagnetic wave, we can describe the various colors in terms of either the frequency f or the wavelength lambda of the wave in this figure. We illustrate the oscillations present in a monochromatic electromagnetic wave, polarized so that the electric oscillations are in one plane. The wavelength and frequency of the monochromatic wave are inversely proportional to each other, with the proportionality constant as the speed of light c. C equals lambda f. Frequency is constant for all materials, but the speed of light and the wavelength are material dependent. In a vacuum, C equals 3 into 10 to the power of 10 centimeters per second. Light wavelengths are very small, so length units for designating spectral colors are usually either angstroms, 1 angstrom equals 10 to the power of minus 8 centimeters, or nanometers, 1 nm equals 10 to the power of minus 7 centimeters. An equivalent term for nanometer is millimicron. Light at the red end of the spectrum has a wavelength of approximately 700 nanometers nm, and wavelength of the violet light at the other end of the spectrum is about 400 nm. Since wavelength units are somewhat more convenient to deal with than frequency units, spectral colors are typically specified in terms of wavelength. A light source such as the sun or a light bulb emits all frequencies within the visible range to produce white light. When white light is incident upon an object, some frequencies are reflected and some are absorbed by the object. The combination of frequencies present in the reflected light determines what we perceive as the color of the object. If low frequencies are predominant in the reflected light, the object is described as red. In this case, we say the perceived light has a dominant frequency or dominant wavelength at the red end of the spectrum. The dominant frequency is also called the hue or simply the color of the light. Other properties besides frequency are needed to describe the various characteristics of light. When we view a source of light, our eyes respond to the color or dominant frequency and two other basic sensations. One of these we call brightness, which is the perceived intensity of the light. Intensity is the radiant energy emitted per unit time, per unit solid angle, and per unit projected area of the source. Radiant energy is related to the luminance of the source. The second perceived characteristic is the purity or saturation of the light. Purity describes how washed out or how pure the color of the light appears. Pastels and pale colors are described as less pure. These three characteristics, dominant frequency, brightness and purity, are commonly used to describe the different properties we perceive in a source of light. The term chromaticity is used to refer collectively to the two properties describing color characteristics, purity and dominant frequency. Energy emitted by a white light source has a distribution over the visible frequencies as shown in this figure. Each frequency component within the range from red to violet contributes more or less equally to the total energy, and the color of the source is described as white. When a dominant frequency is present, the energy distribution for the source takes a form such as that in this figure. We would now describe the light as having the color corresponding to the dominant frequency. The energy density of the dominant light component is labeled as ED in this figure, and the contributions from the other frequencies produce white light of energy density EW. We can calculate the brightness of the source as the area under the curve, which gives the total energy density emitted. Purity depends on the difference between ED and EW. The larger the energy ED of the dominant frequency compared to the white light component EW, the more pure the light. We have a purity of 100% when EW is 0 and a purity of 0% when EW equals ED. When we view light that has been formed by a combination of two or more sources, we see a resultant light with characteristics determined by the original sources. Two different color light sources with suitably chosen intensities can be used to produce a range of other colors. If the two color sources combine to produce white light, they are referred to as complementary colors. Examples of complementary color pairs are red and cyan, green and magenta, and blue and yellow. With a judicious choice of two or more starting colors, we can form a wide range of other colors. Typically, color models that are used to describe combinations of light in terms of dominant frequency, hue, use three colors to obtain a reasonably wide range of colors, called the color gamut for that model. The two or three colors used to produce other colors in such a color model are referred to as the primary colors. No finite set of real primary colors can be combined to produce all possible visible colors. Nevertheless, the three primaries are sufficient for most purposes, and colors not in the color gamut for a specified set of primaries can still be described by extended methods. If a certain color cannot be produced by combining the three primaries, we can mix one or two of the primaries with that color to obtain a match with the combination of remaining primaries. In this extended sense, a set of primary colors can be considered to describe all colors. This figure shows the amounts of red, green and blue needed to produce any spectral color. The curves plotted, called color matching functions, were obtained by averaging the judgments of a large number of observers. Colors in the vicinity of 500 nm can only be matched by subtracting an amount of red light from a combination of blue and green lights. This means that a color around 500 nm is described only by combining that color with an amount of red light to produce the blue-green combination specified in the diagram. Thus, an RGB color monitor cannot display colors in the neighborhood of 500 nm. Solved problems. The color of an object is largely determined by its diffuse reflection coefficient. If KD equals 0.8, 0.4 and 0 and the light is blue, what is the color of the object? Black, since the object does not reflect blue light and there is no red and green light for it to reflect. What is the color of the object if magenta light is used? Red, since the object only reflects the red component of the magenta light. Why does everything look gray or black in a dark room where we can barely see? The color-sensitive cones in our eyes do not respond well to low-intensity light. On the other hand, the rods that are sensitive to low-intensity light are colorblind. What is the difference between Y in CMY and Y in YIQ? The Y in CMY means yellow, whereas the Y in YIQ represents luminance. RGB color model. Based on the tri-stimulus theory of vision, our eyes perceive color through the stimulation of three visual pigments in the cones of the retina. These visual pigments have a peak sensitivity at wavelengths of about 630 nm red, 530 nm green, and 450 nm blue. By comparing intensities in a light source, we perceive the color of the light. The theory of vision is the basis for displaying color output on a video monitor, using the three color primaries, red, green, and blue, referred to as the RGB color model. We can represent this model with the unit cube defined in R, C, and B axes, as shown in this figure. The origin represents black and the vertex with coordinates 1, 1, 1 is white. Vertices of the cube on the axis represent the primary colors, and the remaining vertices represent the complementary color for each of the primary colors. As with the X, Y, Z color system, the RGB color scheme is an additive model. Intensities of the primary colors are added to produce other colors. Each color point within the bounds of the cube can be represented as a triple RGB, where values for R, G, and B are assigned in the range from 0 to 1. Thus, the color C lambda is represented in RGB components as C lambda is equal to RR plus CG plus BB. The magenta vertex is obtained by adding red and blue to produce a triple 1, 0, 1, and white at 1, 1, 1. Is the sum of the red, green, and blue vertices. Shades of gray are represented along the main diagonal of the cube from the origin, black to the white vertex. Each point along this diagonal has an equal contribution from each primary color, so that a gray shade halfway between the black and white is represented as 0.5, 0.5, and 0.5. The color graduations along the front and top planes of the RGB cube are illustrated in this figure. Chromaticity coordinates for an NTSC standard RGB phosphor list are listed in this table. Also listed are the RGB chromaticity coordinates for the CIE RGB color model and the approximate values used for phosphors in color monitors. This figure shows the color gamut for the NTSC standard RGB primaries. YIQ color model. Whereas an RGB monitor requires separate signals for the red, green, and blue components of an image, a television monitor uses a single composite signal. The National Television Systems Committee NTSC color model for forming the composite video signal is the YIQ model. Luminance brightness information is contained in the Y parameter, while chromaticity information, hue and purity, is incorporated in the I and Q parameters. A combination of red, green and blue intensities are chosen for the Y parameter to yield the standard luminosity curve. Since Y contains luminance information, black and white television monitors use only the Y signal. The largest bandwidth in the NTSC video signal, about 4 MHz, is assigned to the Y information. Parameter I contains orange cyan hue information that provides the flesh tone shading and occupies a bandwidth of approximately 1.5 MHz. Parameter Q carries a green magenta hue information in a bandwidth of about 0.6 MHz. An RGB signal can be converted to a television signal using an NTSC encoder, which converts RGB values to YIQ values, then modulates and superimposes the I and Q information on the Y signal. The conversion from RGB values to YIQ values is accomplished with the transformation as shown. This transformation is based on the NTSC standard RGB phosphor, whose chromaticity coordinates were given in the preceding section. The larger proportions of red and green assigned to a parameter Y indicate the relative importance of these hues in determining brightness compared to blue. An NTSC video signal can be converted to an RGB signal using an NTSC decoder, which separates the video signal into the YIQ components, then converts to RGB values. We convert from YIQ space to RGB space with the inverse matrix transformation, as shown on the screen. Conclusion. In this chapter, we have covered the following in detail: properties of light, intuitive color concepts, RGB color model, YIQ color model, CMY color model, HSV color model, conversion between HSV and RGB models, HLS color model.